So in this video, I want to cover special relativity and just give you a general summary of the important concepts or ideas that you want to retain when you're approaching problems about special relativity. So this is really about the understanding that you need to have around it. Now, special relativity rests on Einstein's two postulates. So you must be familiar with these two postulates. Now, the first postulate that Einstein states is 1. The laws of physics remain the same, or they're retained, in all inertial frames of reference. Now, we have spoken about this term about inertial frames of references, but it is really important that we understand what is meant by inertial frames of reference. It means two bodies that are moving in the same direction at the same speed. And therefore, when you have a look at length, time, mass, and compare those between the two frames of references, there's no change, and the classical laws of physics apply. However, what really becomes problematic is when we have what's termed non-inertial frames of reference. That's when one frame of reference is moving either faster or slower or in an opposing direction to the other. And then the laws of classical physics get a little bit scrambled, and this is where special relativity comes into play. The second postulate of Einstein is that the speed of light is constant. And it's constant throughout the universe. Now, if we break this concept apart a little bit further, what we could say is if I had a car, and this is the really important thing about Einstein, and let's say that this car had its lights on, like so. And obviously from the lights, it's ejecting a photon. Now, this car at the moment, its velocity is 0. So therefore, we would expect this photon to be moving with a velocity of c, this photon. However, if we have the car moving, and this is where the second postulate becomes really important, and let's say that I give it a velocity of, let's say, 300 kilometers per hour. Yeah. So it's moving quite fast, but in comparison to the speed of light, it's actually very slow. Well, if we're talking about classical laws of physics, we'd expect that the velocity of the photon would be c, the speed of light, plus 300 kilometers per hour. Okay? However, this is most definitely not the case. What we find is the velocity of the photon is still given as c, and this gives us the insight into the speed of light being, if you like, a universal speed limit. Now, I know in previous classes I've talked about, if you like, a pixelated kind of version of reality or version of the world. For our purposes for Year 12 physics, and given everything that's going on, don't worry about that so much. What you need to understand is just these two postulates. Okay, so then we go a step further, and we've got to talk about how we go about solving problems. Well, the key to solving problems involving special relativity is you need to understand the Lorentz factor. And you need to be able to work with the Lorentz factor quite easily. Now, in some problems, they will give you the Lorentz factor. Other problems, you'll need to derive it. You'll need to understand that the Lorentz factor is given by this. I have a follow-up video which talks about how the Lorentz factor is derived. The second thing that you need to understand is the effect of special relativity on time dilation, length contraction, and a thing that we call relativistic mass. Now, all of this here talks about non-inertial frames of reference. Pretty much you can be guaranteed, if you're having a question to do with special relativity, you're going to have to be dealing with non-inertial frames of references. Okay, so you need to have an understanding of all of those concepts. Now, if we're talking about time dilation, you need to understand this, and I'm going to write this out very slowly, and I want you to read it, but you really need to have this cemented within your thought processes when you're approaching problems to do with time dilation in the context of special relativity. Okay, so the rate of time, okay, is slower, and I'll just highlight that for you, okay, in a moving frame of reference compared to the stationary frame observing it. Now, I'm not sure what you'll need to do to really understand or to really, learn this concept off by rote. You may want to write it out 20 times just so that you're understanding it. You may want to do further reading on it, but you must understand the rate of time is slower in a moving frame of reference compared to the stationary frame of reference observing it. Now, if I was going to give you an example, we could say that we had, we'll see how good my artistic flair is here. Okay. So here we have planet Earth. Okay. Put a little bit of ocean in it. Okay. Which makes it look quite neat. We're going to have a person who is our observer looking here. And we're going to say this age of the person is 30 years. Okay, and then we're going to have another person in a rocket ship. Obviously, this rocket ship is moving with a speed. Okay, we'll say that speed is a significant fraction of the speed of light. And we're going to say that the age of this person is also 30 years. Okay, so let's fast forward time. Okay, let's say 10 years. Now, obviously on Earth, what we would find, I don't want to get too precious with my drawing, but I don't mind doing it either. what we find is this person observing it, the age, as we know, would be 40 years. Obviously 30 plus 10 equals 40 years of age. However, the person in the rocket ship, okay, their age will be less than 40 years. Why? Because time for them has gone slower than the respective time to the person here on planet Earth. So they've actually been able to, if you like, hold on to their youth a little bit longer, which is a nice concept, something that we're all striving for, I guess. All right. The other concept that we need to appreciate is length contraction. And length contraction is somewhat easier than time dilation, but you must remember when an object moves, its length shrinks compared to those in a stationary frame of reference. Okay. For this, what the real idea is, you must distinguish or determine proper length. Now, proper length is commonly denoted as L0. Okay? And the way that we distinguish this is it's measured, proper length is measured by an observer who is at rest relative to 2 points. Okay, so let's consider a person moving on a train, V. Here we have it. You know, the train's moving. We can call this point A, point B, and for this person, we can say that proper length is given by LO. However, if you're standing outside of the train, here, as an observer, okay, you're watching the train pass, and you are not at rest respective to point A's and point B. This observer within the moving frame of reference here, just highlight here, okay, they're stationary, or they're at rest to points A and B. And that's what you need to really understand moving forward. Pardon the pun. Now, the last aspect of special relativity, and probably one aspect that we haven't really got a lot done in class, is this thing called relativistic mass. And it's quite simple, okay? So when a body moves, okay, or moves, and I'll just write has a velocity or momentum, then it gains mass. And this is expressed by M equaling MO times Lorentz. Okay, the Lorentz factor. And MO is given by, or a thing which we call the resting mass. So it's the mass of the body when it's at rest. Now, an important side note is that a body that has non-zero mass cannot move at the speed of light. Now, why is this statement important? Well, it's important when we consider photons, because photons are largely described as particles that have no mass, and in this aspect, photons have non-zero mass. Therefore, they can move at the speed of light, and they are a form of energy that moves at the speed of light. Okay, so that's a special relativity quite quickly covered for you. It's just a summary. Make use of it as you will.